Our project is called Design and Development of a Gesture Controlled Drone. So, what exactly is a gesture controlled drone? Simply put, it's a drone that can be flown using human hand gestures instead of a traditional remote controller. To make this possible, we used a combination of technologies: media pipe for hand tracking movements, OpenCV for processing the camera images, Python for recognizing the gestures, and an ESP32 module along with Wi Fi to wirelessly send commands to the drone. Our problem statement is, why are we doing this? So, now why did we choose to work on this? Traditional drone controllers require a fair amount of training and technical know how to operate. This makes them difficult for beginners to pick up. They also rely entirely on physical remote, which limits how naturally a person can interact with the drone. Overall, this creates a real barrier for anyone who wants an intuitive, easy way to fly a drone. And that's the gap we wanted to address. To solve this, our system controls the drone using just a laptop camera, real hand time gesture detection, and wireless communication through an ESP32 module, removing the need for a physical controller altogether. Goals, alternatives, and prototypes. Our goal was to build a system that could recognize hand gestures in real time and translate them directly into drone movements. Things like moving forward, backward, up, down, left, and right just by bending different fingers. Before settling on this approach, we looked at existing alternatives like standard RF remote controllers and app-based controls, but these still depend on physical hardware and don't offer a natural hands-free way to interact with the drone. We also explored different prototypes along the way, testing how gesture data could be processed using OpenCV and MediaType, and how reliably we could transmit those commands over Wi-Fi to the ESP32 before settling on a final pipeline. Our target audience. So, who is this actually for? Our target audience is essentially anyone who wants to fly a drone without going through the steep learning curve of a traditional controller. Beginners, hobbyists, and even educators who want a more interactive way to demonstrate drone technology. This is helpful because it lowers the barrier to entry, makes drone operation feel more natural and intuitive, and opens up drone control to people who might otherwise find it inaccessible. That's the core of it.
And I'll be walking you through how we converted human hand gestures into real-time flight physics. Our software pipeline completely eliminates the need for a physical remote controller. Instead, a standard webcam captures video frames at 30 frames per second. We process these frames using OpenCV for image manipulation and MediaPipe's 21-point hand landmark tracking. The absolute coordinate changes of these landmarks are then mapped directly to flight commands. To safely validate our software before deploying it to real hardware, we use a Python-based 3D simulation environment. In this case, we are using PySimverse. The simulator handles full rigid body dynamics, mapping the true weight distribution of our components, including our ESP32 S3 mini microcontroller, MPU 6050 IMU, and the microframe. A Python control loop acts as our virtual flight controller, reading simulated gyroscope data from the MPU and calculating real-time mathematical corrections to keep the drone level. Now, let's look at the step-by-step execution of our gesture dictionary in the simulation. Before we begin, first we have to show an open palm to the camera. It will assign the landmarks to all the joints on our fingers. Now, I bend my index finger down. This is my gesture 1. When the pipeline recognizes a bent index finger, it sends a signal to all four motors to increase thrust and move up vertically. Gesture 2. This is where I bend my middle finger down, and similarly it tells this of all four motors to decrease thrust and move down vertically. Gesture 3. This is where I bend just my ring finger, and it tells the microcontroller where the left two motors receive a signal to decrease throttle and right two motors to increase throttle, allowing the drone to tilt to the left and move in the left direction. Gesture 4, in the simulated fashion, where I bend my pinky finger, it tells the right two motors to decrease throttle and left two motors to increase throttle, allowing the drone to move to the right. Gesture 5 is where I bend my thumb finger to my palm, and it tells back two motors to increase thrust and front two motors to reduce thrust in order to allow the drone to move forward. And finally, gesture 6 is where I bend all five fingers of my palm, and this tells the drone to reduce thrust for back two motors and increase thrust for the front two motors to allow the drone to move backwards. Now we need a condition to stop the movement. This is where I press Q and it stops the hand gesture control and slowly decreases power on all four motors to land safely. Thus, by utilizing the simulation framework, we successfully closed the sim to real gap, verifying our computer vision algorithms and control loops without a single physical crash. Next up, my teammate will discuss the hardware integration. Thank you.
Hello everyone, this is Balaji. Today I am going to explain you about the hardware components used in our project. First we have the drone frame. The drone frame is the body of the drone. It holds all the components together and keeps the drone strong and lightweighted. Next is the ESP32S3. This is the main controller, or we can say the brain of the drone. It receives the control signals from the laptop through Wi-Fi and sends command to the motors based on the hand gesture. The next component is the coreless DC motors. We use four motors in our drone. These motors rotate at very high speed and provide the power needed for the drone to fly. They are lightweight, which makes the drone more efficient. Attached to the motors are the propellers. When the motors spin, the propellers create thrust. This thrust lifts the drone into the air and helps it move forward, backward, up and down. Next is the lithium ion battery. It is the power source of our drone. It supplies electricity to the ESP32 motors and all other electronic components. Finally, we have the laptop with a camera. The camera captures the user hand gestures. The laptop processes this gesture using OpenCV and converts them into control commands. These commands are then sent wirelessly to the ESP32, which controls the drone. Thank you.
Expected outcomes. Now let's look at the expected outcomes of our project. By the end of this project, we expect to achieve real-time gesture recognition, meaning the system will able to detect and interpret the hand gesture instantly without any noticeable delay. We also expect to achieve reliable wireless drone control where commands are transmitted from one laptop to the drone seamlessly over Wi-Fi. This leads to our next outcome, improved human-drone interaction, making entire experience feel more natural and intuitive for the users. Another key outcome is reduced dependency on the traditional remote controllers, since our all system replace the physical controllers with the simple hand gesture. And finally, all this comes together to give us user-friendly drone operating system, one that even a complete beginner can operate without any single prior training. Gantt chart. Moving on to our project timeline, which was originally planned over 13 weeks. Week 1 through 3 went schedule. We completed our litera- literature survey, analyzed the requirement, and set up the development environment. From the fourth week onwards, we focused entirely on the software side of the project. We successfully integrated media pipe for hand landmark detection, implementation, gesture recognition using OpenCV, and mapped each recognized gesture to its corresponding drone control command. We completed the command transmission and reception logic and tested this part of the system thoroughly to make sure the gesture recognition works accurately and responds in real time. So on the software front part, our project is fully completed. However, we came it to the hardware and build stage, actually assembling and integrating the physical drone. We ran into some challenges getting ESP32 communication working reliable with the actual hardware along with the mechanical assembly of the drone turned out to be more time consuming than we initially planned. We took guidance and support from our seniors to work through these issues. We still in the progress of finalizing this part. So at this stage our software module is integrated and final build is still ongoing, and we expect to complete it within the additional time and the support we received it. Thank you.
So we moving on to the components and their costs. For this project, our total budgeted funding was 10,000 rupees, out of which we have spent 2,040 rupees. So far, that's about 20.4% of our budget. The major expenses include the drone chassis, which we have got 3D printed, costing 750 rupees. That's the single biggest expenses at almost 37% of our spending. Next is ESP32, it's cost around 370 rupees, which handles our wireless communication. We spent 400 rupees on 4 coreless motors and 200 rupees on a 3.7 volt of lithium ion battery to power the drone. We also used 150 rupees for IMU module for motion sensing and 80 rupees on 8 MOSFETs and 60 rupees on 4 propellers. The remaining components, flyback diodes and capacitor were minor purchase around 10 rupees each. Overall, this shows our project has been cost effective, staying well within budget while covering all essential hardwares needed for the gesture control drone. And references. Finally, here are the references that supported our project. We referred the Practical Python and OpenCV third edition by Dr. Adrian Rosbrook for image processing techniques. We also used official media pipes, tasks, API documentation, and OpenCV documentation for implementation guidance. For simulation purpose, we referred to the PySumverse simulator documentation. We also studied a 2025 publication titled Enhancing Drone Navigation and Control, gesture based piloting, obstacle avoidance, and 3D trajectory mapping, which gave us insights into recent advancement in this field. Lastly, we refer to small unmanned aircraft theory and practice by Baird and McLean, published by Princeton University Press for the theoretical foundation of drone control system. Thank you.